Well, if you can have a first derivative test, you can have a second derivative test. The first derivative test focuses, oddly enough, on the first derivative. The second derivative test, oddly enough, focuses on the second derivative. So the second derivative talks about concavity, whether your function is concave up. Colloquially, we talk about the function holding water. Concave up, the function holds water, versus concave down, that's not what we want. Concave down, the function spills water. That's the colloquial way to talk about concave up, concave down. Mathematically, we talk about whether f prime is increasing or decreasing. If f prime is increasing, f is concave up. Whether the function itself is increasing or the function itself is decreasing. In this case, f is increasing. In this case, f is decreasing, but it does not matter. In both of these cases, the derivative goes from smaller values to bigger values. That's a large negative number. That is a less negative number. So the derivative is increasing. And if the derivative is increasing, then the function is concave up. So this is awful. This should say f is concave up. F is concave up. F is concave down. That does say f is concave down. In this case, the derivative starts big, gets small. Small negative, large negative. The derivative values from left to right are decreasing, and so the function is concave down. So what does that tell us? Well, if f prime is increasing, then f double prime is positive. If f double prime is positive, f is concave up. Similarly, if f double prime is negative, f is concave down. It is super important to keep your f prime, and your f double prime straight. F is concave up, f prime is increasing, f double prime is positive. F is concave down, f prime is decreasing, f double prime is negative. That's super important because you're going to have to keep track of f's and f primes and f double primes, and somebody on a test is going to write it instead of f or f prime or f double prime. That's going to make me all sorts of upset. Okay, so here's your picture. In this area, the function is concave up because its derivative values are increasing. Negative, positive, 0, positive. These derivative values are increasing, so the function is concave up. In this area here, the derivatives start positive, then they hit 0, then they go negative. In this area, the function is concave down. The slope is increasing, the slope is decreasing. When the slope is the slopiest, when the slope changes from increasing to decreasing, that point is called an inflection point. If f is continuous and changes concavity, we call that point an inflection point. So that's something you have to know. I'm going to ask you about inflection points. You're going to say, hey, find the inflection points of whatever, and you're going to have to do that. It's not too bad. If the point is an inflection point, almost always f double prime is 0. Rarely, f double prime will not exist. Most of the time, f double prime is 0. And in case you're watching and not listening, there's a visual cue. Okay? Okay, so an example might be in order. Find intervals of concavity for f of x is x cubed minus 3x squared plus 12. So intervals of concavity. Intervals of concavity depend on the second derivative, so you have to take one derivative to get a second derivative, right? So this is the second derivative. Intervals of concavity. So f double prime only changes sign at one particular place. On the right side of 1, f double prime is positive. On the left side of 1, f double prime is negative. So if f double prime is negative, f is concave down. And if f double prime is positive, f is concave up. So we would say that f is concave up on 1 to infinity because f double prime is positive there. Similarly, we would say f is concave down on negative infinity to 1 because f double prime is negative there. So, let's do something else first. So, the second derivative test. Have some function. The function has a min and a max. Here's where the min is. Here's where the max is. At both the min and the max, the tangent line is flat. Notice the concavity at this point. In this interval containing this point, f double prime is positive. And in this interval containing this point, f double prime is negative. Function's concave down, it's got a max. Function's concave up, it's got a min. And that is all in the second derivative test. Second derivative test assumes that f double prime is continuous, that it exists everywhere. If the second derivative is positive and the first derivative is 0, then you have a min. If the second derivative is negative and the first derivative is 0, then you have a max. That's not trivial. If the second derivative is itself 0, we conclude nothing. We go back, we try the first derivative test, we try something different. If the second derivative is 0 and the first derivative is 0, then we do not know anything. Find all extrema for h of x equals x to the fourth minus 4x cubed. So we look for the places where the first derivative is 0. That seems right. First derivative is 0 when, well, it appears that x equals 0 is one of the points and x equals 3 is the other. So we take a look at the second derivative. The second derivative is 12x squared minus 24x. So I've got two values of x where the tangent line is flat. What is the second derivative at those points? Well, h double prime of 0, that's 0. And h double prime of 3, that's 9108 minus 72, that's 36. So here's what we know. X equals 3 is a min because h prime of 3 is 0 and h double prime of 3 is positive. Concave up with a flat tan, that's a min. I don't know anything about that. I don't know anything about that because the second derivative test is inconclusive because the first derivative is 0 and the second derivative is 0. I don't know anything about that. So we would go back and use the first derivative test, and we would see on the first derivative test, taking a look at h prime, taking a look at this function, On the left side of 0, that's negative. Between 0 and 3, that's negative. On the right side of 3, that's positive. So the derivative h prime does not change sign at 0. And so we know from the first derivative test that this is neither a max nor a min. There are questions that are posted in the Canvas lesson, things you should practice from the Strang book before you come to class. I look forward to seeing you.